In this video, we're going to continue our discussion of chirality as it applies to molecules and really get into this idea of stereochemistry. So what I want to do is bring back up that definition of stereochemistry. So stereochemistry, we had one definition, but now that we have a better appreciation for chirality, I want to put it in the context of chirality. Stereochemistry is the study of chirality as it applies to molecular systems, as it applies to molecules. Now, a really good question I get at this point is, as students are kind of grinding through looking at molecules and seeing if they have carbon atoms with 4 different things attached to it, is what's the purpose of this? Okay, we looked through chair structures. That felt a little archaic. Maybe arcane is a better word. Just difficult to wrestle with. It doesn't look a lot like what I envisioned a chemistry education to be. But then I reminded us that the 6-membered ring is so abundant, so prevalent in nature. Diamonds exist as chair structures. Sugars exist as chair structures. We really need to understand how chair structures work to gain an appreciation for how these types of chemical systems behave. Well, similarly, what we have to recognize is that so many chemical systems, particularly what we call organic molecules, molecules centered around the element carbon, are chiral. Now, something emerges when we're looking at chiral objects. So just in general, why chirality in general? Why stereochemistry? Chiral objects interact with other chiral objects differently. That's really important. That's the key takeaway from this. Let's talk about that for a second. If we have our hands, left and right hand, we talked about how they are chiral because the mirror image, which is just the opposite hand, the mirror image, while it appears to be the same, it's just a mirror image. And it's nothing else. We cannot get them to superimpose. They are not the same. Now, how does that impact us in real life? Well, for the most part, we're interacting with non or achiral objects. For example, if we grab a pencil, yes, there's some different muscle memory in my left hand and my right hand, so I'm not as able to draw as well with my left hand. But that's not what I'm talking about. I'm talking about, let's envision we're perfectly ambidextrous. And if we are, we can do everything just as well with our left hand as our right hand. Okay, so I could write perfectly. If I could play basketball, I could dribble just as well with my right hand as I could with my left hand. And making shots would be no problem either. Basketball is achiral. The pencil is achiral. Many things are achiral. Let's talk about some things that are chiral. Like, for example, if you grab like one of those fancy pairs of scissors, you put it in your right hand, you're like, oh, this feels a little bit nicer than the typical pair of scissors. I feel like I could cut longer. And then you cut. But even though you're ambidextrous, if you stick it in your left hand, it feels miserable, like there's grooves in the wrong places. It's like it wasn't designed for you. Turns out that pair of scissors, we call a right-handed pair of scissors, is chiral. If we held it up to a mirror, that object would be a mirror image object, and it would not be superimposable on the scissors. How do I know that that mirror image object would not be superimposable? Because we've made it. We've taken that fancy pair of scissors, and we've actually made the enantiomer, made the mirror image of that structure, okay? We've made the mirror image, and as a result, we have these 2 scissors, and we can kind of show that they're not superimposable. Now, why did we make that mirror image? Well, that's because we had so many people that were left-handed saying, hey, I'm a lot stronger with my left hand. I would like a comfortable pair of scissors. And all the scissors manufacturers said was, oh, well, the left hand just wants a left-handed pair of scissors, which is the mirror image of the right-handed pair of scissors. And that's what we did. Here's a way better example, something that we deal with all the time, something that makes this lecture a little bit less satisfying. It's a bit more iconic when we do it in person. And that is, if you think about it, our shoes are chiral. Our shoes are mirror images of each other, but we can't get them to superimpose. In fact, we label one as a left-handed shoe and a right-handed shoe. Now, what I typically like to do in this lecture is actually give the entire 15-minute lecture with the shoes on the wrong feet. Something like I was inspired by my kids when they were like 2 and 3. They always wear shoes on the wrong feet. And I was like, man, that must be uncomfortable. But it's the reason why it's uncomfortable is because of chirality. It's because that chiral objects interact with other chiral objects differently. So the mirror images of each shoe, the left and the right shoe, interact with the right foot differently. One feels great, one feels awful. And if you give a 15-minute lecture, your knees hurt, your feet hurt, your back hurts. It's kind of miserable. But it really proves the point, or sells the point, that chiral objects interact with other chiral objects differently. And that's why chirality. Now, why in the context of this class and not like some physics class or something? It's because a lot of the molecules in our body, particularly the proteins, are chiral. So they're chiral. So what? Well, a lot of the small molecules, a lot of the organic molecules that we consume to interact with these proteins are also chiral. And if we're not sure what's going on at the molecular level in terms of the chirality, we could screw up. And unfortunately, we have screwed up in big ways. We've handed people the wrong mirror image structure of a molecule, and it's interacted with the proteins in our bodies in dire ways, ways that we'll look at have led to severe consequences. And so knowing stereochemistry, knowing chirality is critical, especially if you want to pursue a future in medicine or some sort of molecular science. We have to understand this stuff. We have to know this stuff. The FDA has gotten a lot better at it. But again, I'm speaking to many people that want to be future practitioners of medicine. And so understanding chirality is critical in the pharmaceutical world. Okay, so let's get into it. What I want to talk about is the idea of stereoisomers. So I'm using that suffix isomer again. And what that means is that we're going to have to consider molecules with the same, molecules plural. Again, it's not just one, it's multiple if we're talking about some form of isomer, isomerism. Molecules, so at least two, with the same composition. That's true of any isomer. So all I'm doing is just providing the first part of the definition of any isomer. They're going to be molecules, more than one, with the same elemental composition. So carbons, hydrogens, whatever, they're all the same count, the same composition, that differ in the arrangement of atoms in 3 dimensions. And then the caveat here is not due to free rotation. So if it was just a difference because one single bond did free rotation 60 degrees, the other one stayed put, that would be a conformational isomer that we looked at in the last module. Here we're talking about a stereoisomer, which here we have the arrangement of atoms differing in 3-dimensional space. One way to talk about this, and it's not the only way, but it's a really helpful way as we get started, is we're going to be talking about differences in wedge and dash, and differences at stereocenters and chiral carbons. Okay, so differences in the wedges and dashes, the orientation at stereocenters / chiral carbons. That's more of a slash than an and. There's stereocenters, chiral carbons, mostly the same for us. Okay, there's 2 types of stereoisomers, and they have ridiculous names for students in their first semester of organic chemistry to try to learn. So just practice it, try to enunciate it as best that you can. But the 2 types of stereoisomers are as follows. Number 1, we have enantiomers. Number 1, we have enantiomers. Number 2, we have diastereomers. Enantiomers, diastereomers. Okay? So again, not the easiest words to kind of say the first time that you learn them, but 2 very important words that we should get comfortable with. So what we're going to do is talk about the general gist of these things now, and then we will get into more specifics on them in the next 2 lectures. So enantiomers structures that are enantiomers differ as follows. okay? So they differ as follows. Now I said that in general, this is a class of stereoisomers, so we're going to be different in our three-dimensional arrangement, but we're going to be more specific so that we can tell the difference between enantiomers and diastereomers. Number one, they have flipped all wedges and dashes. So this is sort of a shortcut. We'll look at this and we'll practice this, but we're going to flip all wedges and dashes. I like to get people thinking about that in a lot, as early as we can. So they differ as follows. They flipped all the wedges and dashes, and they differ in how they interact with other molecules, with other chiral objects, let's say. Because a chiral object doesn't have to be a molecule. It could be like our hands and feet and stuff. Okay, so we flipped all wedges and dashes, and we differ in how we interact with other chiral objects. So, okay, now how they're similar. Enantiomers are similar in ways that are very surprising. Okay, so these things are similar in most physical properties. This is sort of crazy. They are similar slash, I should just cross that out because similar kind of implies maybe it's different. When I say similar, I mean the same in most physical properties. If you took their boiling point, melting point, physical properties, color. If you think of most physical properties, they're the same. That's kind of wild because again, these are different molecules. They differ in the three-dimensionality. Okay, we can't get these things to superimpose. Yes, they have the same composition. Yes, they have the same connectivity, but their arrangement in 3 dimensions is different. So these are different molecules. It's like taking 2 molecules, and no matter what you do, they boil at the same temperature. If you think, as we do the simple distillation experiment, this module, they boil at the same temperature. That's kind of crazy, okay? I mean, completely different molecules. No matter what you do, how precisely you want to look at the boiling point range, they will boil at the same temperature. If it's a solid, they will melt at the same temperature. So many physical properties will be the same. Now, some crazy things, though, is how they interact with chiral objects like us differs. No matter how much we try to make it the same. Like, for example, the receptors in our nose are chiral. They're made up of chiral molecules. And so when we smell enantiomers, 2 molecules that happen to be labeled as enantiomers, we could get different smells. So we'll look at some examples of that later. Now, how are molecules become stereoisomers? Well, I hinted that you would take all of the wedges and we flip them. Flip all wedges and dashes. That works a lot. That works a lot. There are some cases where it doesn't, but the better definition is these are mirror image stereoisomers. And that is enantiomers. Enantiomers are mirror images of each other. That gets the highlight, the star. We have to know that. We have to associate that when we're talking about a specific type of stereoisomer event, that is 2 molecules, and we say that they're stereoisomers, okay? Those molecules must be mirror images. Now, let's think about that. That means that a chiral molecule can have only 1 enantiomer. Whereas, in constitutional isomers, we had like multiple. It got overwhelming in some cases. But no matter what the molecule is chiral. It has 1 enantiomer. and only one enantiomer. So all, I can't think of an example that doesn't, all chiral molecules have one enantiomer. All chiral molecules have one enantiomer because we're not like, we don't have these magic molecules that don't appear in the mirror. So by definition, enantiomers are mirror image stereoisomers. So if you have a molecule, you can hold a mirror up to it and get an image out. Now you only get one. You can't have more, right? There's not like multiple funhouse mirrors or something like that. It's just a mirror, okay? You can only have one mirror. So you can only have one enantiomer for every chiral molecule. Now, if a chiral molecule doesn't have an enantiomer, what does that say? That says that when you hold it up to a mirror, something would happen, but it's not an enantiomer. Well, I guess if it's a mirror image that's not superimposable, if it's not different, then it's the same. Okay, so if a molecule doesn't have an enantiomer, it's not chiral. All chiral molecules have exactly one enantiomer. If it has 0 enantiomers, it is an achiral object. If it has thousands of enantiomers, then we've broken the laws of the universe by introducing different mirror planes, which we can't do. This mirror object is just one mirror. Okay, I'm getting too far down the rabbit hole. Let's talk about the other type of isomer. So that is diastereomer. Diastereomer. So this typically often originates, but not always, with 2 or more stereocenters. So if you have 2 or more chiral carbons, these are non-mirror image stereoisomers. Okay? These result when some wedges and dashes flip. When some wedges and dashes flip. Okay? Now what's weird about this is some achiral molecules can have diastereomers. It's weird. I don't like to study something like that. I don't like some. We'll look at those in the next module. But some achiral molecules can have diastereomers. Okay. Again, we'll look at this. We'll look at these examples. So some can have diastereomers. Now, additionally, as I started this, I said that di kind of implies 2. So this typically originates when we have 2 stereocenters or more in a molecule. So are there chiral molecules that don't have 2 stereocenters? Yes, certainly. So if we look down here, we had this example. Oh, I didn't highlight that if I rotate this, I get the mirror image. Okay, sorry, I missed that opportunity. If with enantiomers, you can flip all the wedges and dashes and then you can rotate it and show that we have mirror images. We'll get to that in an upcoming lecture. Okay, so some achiral molecules can have stereocenters. It can have, and I should specify, diastereomers. I'm sorry about that. I'm getting too excited because it's getting sort of philosophical, which makes it have a different kind of dimension of fun, right? So I said some. I'm gonna have another some, and I'm going to say that some chiral molecules can have no diastereomers. No, 0 diastereomers. That is, if you draw certain chiral molecules, we just showed one on the previous slide, it can be that you could that molecule is chiral, but it doesn't have any diastereomers. So diastereomers result when you've multiple stereoisomers or stereocenters, and you flip some of the stereocenters, but not all of them. Well, if you only have one stereocenter, you can't flip half of a stereocenter. So you have to flip them all or none. So you either have the same molecule, which is none of them flipped, or you have the enantiomer where all of them flipped. Okay, so some chiral molecules have no diastereomers, and some chiral molecules have many. I mean, like 256, that high. That's fine. So some chiral molecules have many, like more than 100 diastereomers. So it's sort of weird. Now, what I want to talk about is how they're similar and different to each other. So any pair of diastereomers, so we have two molecules, and what I'm saying is we take two molecules and we say that they're diastereomers of each other. Any pair of diastereomers can be similar in what ways? Really, it's composition and connectivity. Composition and connectivity. Well, that's just isomers, right? I mean, and the connectivity, composition, the same number of elements. And in connectivity, well, if they differed in connectivity, they would be constitutional isomers. And we said these are stereoisomers, so it's just three-dimensional arrangement, not due to carbon-carbon single bonds, single bond rotation. How they're different, it turns out, is everything else. In every other way, diastereomers are different. They do not have the same boiling point or melting point. It might be close, like it might be like 118 versus 119, but for enantiomers, it was spot on, no matter how hard you measured it. If it was different, it was not due to something physical in the universe, it was due to us messing up during the measurement. Here, diastereomers, while it might be similar is not the same. I crossed down the previous page of notes, right? Similar means different. Diastereomers differ in every way. How they interact with chiral objects? Yes. How they interact with achiral objects? Yes. They are completely different molecules. So it's these two types of stereoisomers that we're going to try to clarify in the next two lectures as we wrap up Module 3. The key thing to remember is that enantiomers, the E1, okay, enantiomers, these are pairs of molecules. And if we say they're enantiomers, they're mirror images of each other. Diastereomers, non-mirror image stereoisomers. The mirror image doesn't apply, and it can only work if you've got multiple stereoisomers or something else weird is happening, and you flip one and not the other. Okay, we say that they're stereoisomers, but they're nowhere near mirror images of each other. So, a little philosophical, a little overwhelming. I appreciate that, but this will get us into these types of stereoisomers. And understanding how these types of stereoisomers differ is the first big step in really understanding stereochemistry and how ideas of chirality apply to molecular systems and the transformation of matter.